Hey everyone, just going to make a video for our third practice exam. Third. Not going to go over all this stuff, just read it, same as the other ones, just, basic. This is not comprehensive, this is just like a good, check to see, is everything kind of going well. It should give you an idea of things that you should sort of study more after this, and so don't use this as your sole source of studying, but you can use it as a good starting point. Determine the Laplace transform for the following piecewise function. So when you have a piecewise function like this, the first thing you want to do is write this as just a single thing, right? So is equal to 5 times cosine of 2t for t between 0 and 10, and it's equal to 3t to the fourth for t greater than 10. So what you can do is take u10 of t, and then multiply this by 3t to the fourth minus 5 cosine of 2t. And so this is a trick that was just kind of mentioned in the notes for this section. So to write this as like, if you have a piecewise function that's like alpha and then beta, then you could just do like alpha plus like u sub a of t times beta minus alpha. So if basically if t is less than 0, then if t is between 0 and 10, then u sub 10 of t is equal to 0, so this whole thing is 0, so that just kind of goes away. But if t is greater than or equal to 10, then u sub 10 of t is just equal to 1, and so this is just 5 cosine of 2t minus 5 cosine of 2t, so those cancel, and then you're left with 3t to the fourth, which is what you want. So this is what f of x is equal to. So this is something that we can just do the Laplace transform of. So it's going to be just the Laplace transform of all of this stuff. So 5 times the Laplace transform of cosine of 2t plus, I'm very quickly going to run out of room here. Okay, I'm going to just sort of distribute stuff and then go from there. I'll just write this as the Laplace transform of u10 times 3t to the fourth plus, or I'll just say plus Laplace transform of u10 of t times negative 5 cosine of 2t. Okay. 5 cosine of 2t was the Laplace transform. So I'm going to go to the table. Cosine of 2t, so that's going to be the s over s squared plus k squared. Be doing this a lot tonight. 5 times s over s squared plus k squared. So k is just 2 in this case, so that's what we get. All right, what do we get when we have u sub 10 of t times 3t to the fourth? So we need to go back to the sheet and figure out what do we do when we multiply by u sub 10. So u sub 10 shows up in this formula here. Let's copy that, go back up. And let's just use this. All right, so u sub 10 times a function that we know the Laplace transform of, or hopefully, or not necessarily actually. So the Laplace transform of that, I basically pull out an e to the negative as. So a is 10, so e to the negative 10s times L of 3t to the fourth. Oh God. Sorry, I just realized this probably should have been like t squared or something like that. Otherwise, this is kind of terrible. Because this is f of t plus a. So f of t plus a, so this is like f of t, right? So f of t plus a is t plus 10 to the fourth. Yeah. Yeah, okay, that's gonna suck. All right, whatever. u10 of t, or I can actually just do this one too. Move this over. And all right, u10 of t times 5 cosine of 2t. So this is, again, we multiply by e to the negative 10s, and then do the Laplace transform of negative 5 cosine of 2, and not t, but we do t plus a. So t plus 10. Yeah, okay. Yeah, this problem was not very well thought out. These functions here should have been chosen much better. So sorry about that. All right, so let's see. So this is going to be terrible because you can't just, let's see. Is there a formula for like if I'm just doing the Laplace transform of a translation? Let's see. No. No. Yeah. 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 Okay. So this problem is just kind of bad. This is like almost as far as like I'm willing to go here at this point. So here's how you would do this one. T plus 10 to the fourth. Like the only way to really do that would actually to just be like to expand t plus 10 to the fourth. So this is the same as like t plus 10 squared and then square it again. So this is t squared plus 20t plus 100, and then square that. So that's 3 t to the fourth plus 20t cubed plus 100 t squared plus then I would do 20t times everything. So 20t cubed plus 40t squared plus 20 times 100 t, so 2000 t, and then multiply 100 times everything. So 100 t squared plus 2000 t plus 100 squared. So it would be 3 times all of that stuff. And then you could do the Laplace transform of each of these things individually, and it would get you that. And that's how you do this one. Cosine of 2 times t plus 10. This might just kind of suck, actually. Yeah, this was not a well thought out problem, so apologies for that. Anyway, if you understand how to get to like this point, like you will be probably like in a good spot. Yeah, and if you can do this one, then like you're even better. This, I don't think that we have discussed how to do cosine of 2 times t plus 10. Let me just look at the formula sheet real quick, just to double check. Because yeah, we don't really have anything where it's like we're doing the Laplace transform of like, there's no formula for like L of like f of t plus a or something. There's like L inverse of f of t plus a, but not just like L by itself of f of t plus a or minus. Right, so yeah, so we actually kind of get stuck there, which, you know, whatever. Yeah, so if anyway, if I wanted to change this problem so that it is something that's more doable, so first thing I would do would change this to like t squared, or even t. So if I made this t squared, this, it would just be the Laplace transform of this thing right here, which would be, let's just do it. So 3 times the Laplace transform of t squared, which would be 2 over s to the third, plus the Laplace transform of 20t. Maybe I should factor that 3 out from everything. Boop. Laplace transform of 20t would be 20 over s squared, and the Laplace transform of 100 would be 100 over s. Okay, what would the Laplace transform, or what would I change this cosine of 2t to be? Well, I would make it cosine of 2t minus 10. So why would I make it t minus 10 to improve this problem? That would change this to -5 cosine of 2t minus 10. And then in this step right here, we do e to the negative 10s times the Laplace transform of -5 cosine of 2. And now I replace t with t plus 10. So if I were to replace t with t plus 10 for this, I'm going to have t minus 10 times t plus 10. Yeah, so this, let's make that like blue or something. Yeah, so to go from here to here, I replace t with t plus 10, just using this formula up here. So e to the negative 10s times the Laplace transform of f of t plus a. So I just replace t with t plus 10 there. And now this, what would I get? So e to the negative 10s times -5 times the Laplace transform of, well, this is now really just cosine of 2t. So cosine of 2t, that is just s over s squared plus k squared. All right, just the same thing that we did like over here. Oh, even that would actually be kind of bad for this problem, because then this would be different. Yeah, so yeah, you would have to do the Laplace transform of, because this would be different too. All right, yeah, so this is just kind of a bad problem. So anyway, I got like a little too ambitious writing this one, I think, so sorry about that. All right. Determine L inverse of 1 over s to the fourth plus s squared using 2 different methods. Let's find out if this one was over ambitious as well. All right, first thing that you can do, let's see, 1 over s to the fourth plus s squared is equal to what? So I can factor that as s squared times s squared plus 1. So one thing that I could do here is do partial fractions. So I'll write this as a, or I'll do it something over like s squared, right? So it'll be like as plus b over s squared, because the whatever goes up here has to be like degree 1 less than what's down here. And then something over s squared plus 1. So again, this would be like cs plus d, because it has to be like degree 1 less than what's down here. Multiplying through, I would get as plus b times s squared plus 1, and then plus cs plus d times s squared. So this would be a s cubed plus b s squared plus as plus b, and then plus cs cubed plus d s squared. Okay. What do we do now? Now we take all of the cubed terms, so this, and then we'll take all of the s squared terms, this, all of the s terms, and then all of the constant terms, and then just sort of set stuff equal. So we can, first thing that we can say is constant term b has to be equal to 1. Then we can say a has to be equal to 0 because there is no like s. There's no like 0. This is like a 0s over here. And it's like also plus like 0s squared and plus 0s cubed. Plus, so I can say b plus d is equal to 0. And I can say a plus c is equal to 0. And a is 0, so that tells me that c is 0. So a is 0, c is 0, b plus d is 0, so b is 1, so 1 plus d is 0, so d has to be -1. So this is equal to as plus b over s squared plus cs plus d over s squared plus 1, and a is 0, c is 0, b is 1, so I get 1 over s, and d is -1, so I get -1 over s squared plus 1. So I get L inverse of 1 over s minus 1 over s squared plus 1. So if I do L inverse of 1 over s, L inverse of 1 over s is just, oops, not t. L inverse of 1 over s is just 1. Right, if I look at my table, the Laplace transform of 1 is equal to 1 over s, so the inverse Laplace transform of 1 over s is equal to 1. And then the inverse Laplace transform of 1 over s squared plus 1, I forget if it's sine or cosine. 1 over s squared plus 1, that would be sine. Sine of t. So we get that. All right. So that's way number 1. And then the other way, which I hope works, is to write this as product 1 over s squared times 1 over s squared plus 1. Oh, wait. Yeah, okay. So we get L inverse of this. And then we could do the convolution theorem. Get 1 over s squared star L inverse of 1 over s squared plus 1. What's L inverse of 1 over s squared? That is just t. What's L inverse of 1 over s squared plus 1? Sorry, 1 over s squared just gives me t, and then 1 over s squared plus 1 should be sine of t. All right, so then I just have to do the convolution of these two things, and that's the integral from 0 to t of f of tau times g of t minus tau d tau. So this is what the convolution of those two things is. And I'm using like the formula 0 to t f of tau g of t minus tau d tau. That's like our convolution formula. So now I just have to integrate this. And we're going to have to do this using integration by parts. So we'll do u is equal to tau, which would make du equal to 1. dv is equal to sine of t minus tau. I should say d tau over here, just to make it clear that we're like taking derivatives with respect to tau. So v is going to be the antiderivative of sine of t minus tau, which would be cosine of t minus tau. And it is positive cosine, actually. So the derivative of cosine of t minus tau would be negative sine of t minus tau times the derivative with respect to t of t minus tau. The derivative of t minus tau is 0 minus 1, 0 plus negative 1, because the derivative of negative tau is negative 1. So I introduced like a double negative there, so that's why this is positive. So this is equal to uv minus the integral of v du and this is from 0 to t. So I can plug in t for this, so I get t cosine of t minus t, which is 0, minus 0 times cosine of something, doesn't matter, it's just 0. And then minus the integral of cosine of t minus tau. What's the integral of cosine of t minus tau? Well, integral of cosine is positive sine. So this, I think, is going to be, we have to flip the sign. So the derivative of sine of t minus tau would be cosine of t minus tau times derivative of the inside, which is negative 1. So then I have to flip the sign to compensate. Yeah. Okay, and then this is from 0 to t. So we get t times cosine of 0, which is just 1, wait. Hold up. Oh, I messed this up. This was supposed to be s squared. Yeah, so that would be a t. Yeah, this was s squared. I just like forgot to copy this s squared correctly. Yeah, so this is why you do 2 different methods, so you can check your work better. Okay, yeah, this should have been 1 over s squared, which would make this a t, and that's why this is a t. So all right, so things are looking better now. All right, now I plug in t and I plug in 0, so I get sine of t minus t, which is just sine of 0, which is 0, and then minus sine of t minus 0, which is just sine of t. So we get t minus sine of t, which is, you know, the same thing that we got up there if we did it correctly the first time, which we didn't. But we fixed our answer, and then now we got the correct answer. By the way, you could check your answer, or check this answer, by just doing the Laplace transform of this. So the Laplace transform of t minus sine of t is equal to 1 over s squared minus 1 over s squared plus 1, just applying your formulas, and then you could just do find a common denominator here. So you get s squared plus 1 minus s squared all over s squared times s squared plus 1, which is equal to 1 over that denominator, and then that denominator simplifies to this. Great. Solving IVPs. Y prime minus y equals 5 cosine of 2t with y of 0 equals 2. Yeah, if I were being more careful about how I was writing this thing, I would have said solve this IVP using Laplace transforms, and that's probably how you should be approaching this. If I didn't say that, then technically you would be able to do stuff that we did from like chapter 2 or 3 or whatever. Chapter 2, I think, when we did like the integrating factor. So I think doing the integrating factor thing would probably work here. Don't quote me on that, but I think it would. It's been a while. Anyway, so we're gonna apply this formula here. So I'm gonna bring that over because I just want to use it. And then what's the Laplace transform of cosine? All right, so here's what we do. Whenever you have a differential equation like this and you want to solve it using Laplace transforms, you do the Laplace transform of both sides. That's going to be your first step. Okay, so let's do that. Laplace transform of y prime is equal to s times capital Y of s minus y of 0. And then we subtract the Laplace transform of y, which by definition is just equal to capital Y of s. That's just what capital Y is. What's the Laplace transform of 5 cosine of 2t? Well, I can pull the 5 out and then get s over s squared plus 4. Right? Yeah, sine gives me 1 over that. Cosine gives me s over that. All right, cool. Now I plug in my initial value conditions. So y of 0 equals 2. So this is now a 2. I'm also going to try to solve for capital Y. So our second step is really to solve for capital Y in this equation. So I get s minus 1 times capital Y of s. Minus 2 is equal to 5s over s squared plus 4. I could add that 2 over to the other side. Let's just do that. And then divide by s minus 1. So we get 5s over s minus 1 times s squared plus 4 plus 2 over s minus 1. And then our last step is to just take the inverse Laplace transform of both sides. The inverse Laplace transform of capital Y is equal to little y of t. And then we do just whatever L inverse of our right-hand side is equal to. So if I'm doing s over s minus 1 times s squared plus 4, we're going to want to do partial fractions on this. So this is going to be a over s minus 1 plus bs plus c over s squared plus 4. So this becomes s equals, finding a common denominator, a times s squared plus 4 plus bs plus c times s minus 1. As squared plus 4a plus bs squared plus cs minus bs minus c. Let's group terms. A plus b, 4a minus c, and then I'll just like just don't highlight the other terms. So I can say the following. I can say a plus b is equal to 0 because there's no s squared term. I can say b is just equal to 1 because, or sorry, not just b, a plus b. Wait, what am I doing? Let me try that again. Okay, let's look at the s terms. So c minus b is equal to 1. Okay, there we go. And Yeah, and that's just because the coefficient of the s term is just equal to 1. So this is like 1 times s is equal to c minus b times s. And then our constant terms are 4a minus c, and there is no constant term on the left side, so this is just equal to 0. All right, cool. So let's see. So 4a is equal to c. And let's say a is equal to negative b. C is equal to b plus 1. So what's the easiest way to do this? All right, I'm going to sub this into this equation. So this becomes negative 4b is equal to c. And then if c is equal to b plus 1 and c is equal to negative 4b, then b plus 1 has to be equal to negative 4b. So then I can add 4b to the left side, and I get 5b plus 1 equals 0. So 5b is equal to negative 1. B is equal to negative 1 over 5. C is equal to negative 4 times b, so positive 4 over 5. And then A is equal to negative b, which would be positive 1 over 5. All right. Promise the exam's not going to be as complicated as this. In my opinion, at least. Okay, let's see. All right, so then reviewing, this thing is now equal to 1/5 times 1 over s minus 1 plus bs plus c over s squared plus 4. So I can separate that. So let's do minus 1/5 times s over s squared plus 4 plus c, which is 4/5 times 1 over s squared plus 4. I'm going to make that, split that up into 2 times 2 though, because 2 over s squared plus 4 is easier to take the inverse Laplace transform of. Okay, so finally, y of t is equal to L inverse of our right-hand side, which is equal to L inverse of this whole thing plus this. That was fun. Okay, so 1 over 5 times s minus 1, that is 1/5 e to the t, minus 1/5 times s over s squared plus 4. That would be cosine of 2t plus 2/5 times sine of 2t plus 2 e to the t. And maybe you can't do integrating factor method on that. I don't know. Yeah, now I gotta think about whether or not you can do integrating factor method on this. I am genuinely not sure. gotta review that, I guess. Okay. Anyway, hopefully that's right. Let's move on to the next one. All right. We're gonna do this equation again. We're also so we're gonna do like the same steps of take the Laplace transform on both sides, then solve for capital Y, and then do the inverse Laplace transform to get back to little I, which is your solution you're looking for. So do that. You need these things. Just bring that here. All right, so the Laplace transform of the left-hand side is going to be this thing plus this thing, or plus 2 times that thing, plus just capital Y from that. So the Laplace transform of Y double prime is equal to S squared Y of S minus little y of 0 times S minus Y prime of 0 plus 2 times the Laplace transform of Y prime, which is S Y of S minus Y of 0 plus Laplace transform of Y, which is just Y of S. And this is equal to Laplace transform of the right side, which is 5 times delta of t minus 2. I think it's just e to the negative 2s. Here it is. Laplace transform of delta of something, of t minus something, is equal to e to the negative s times that something. So that something was just 2 for us, so e to the negative s times 2. Okay. Now I have to plug in my initial value conditions. So y prime is equal to 0, so I can just get rid of all my y primes. So that's going to go away. And that's it, I guess. And y of 0 is going to be equal to 1. So I can just replace those with 1s. So I get s squared y of s minus s plus 2s y of s minus 2 times 1 plus y of s. Can solve for capital Y of s here. So if I factor out a y of s from this, and this term, I get s squared plus 2s plus 1 times y of s minus s minus 2. Wait. Wait, did I mess something up? Oh, yeah, no, this is, yeah, that's right. That's minus 2. Okay. So we get minus s and then minus 2 and then equals this. Okay, cool. Now I just solve for y of s. So I bring these to the other side. So I get 5 e to the negative 2s plus s plus 2. And that's equal to this. And then now I divide both sides of the equation by this, which ends up giving me this. And so y of t is going to be the inverse Laplace transform of the right-hand side. So I do L inverse of 5 over s squared. Oh, and I might as well just factor that as s plus 1 squared times e to the negative 2s plus L inverse of s over s plus 1 squared. Let's see. plus L inverse of 2 over S squared, or S plus 1 squared. All right. Gotta think. All right. Yeah, okay. I think that the best thing to do here would have been probably to take this S plus 2. So yeah, I'm like trying to think in my head, like how would I do S over S plus 1 squared? And I think if this was S plus 1 over S plus 1 squared, then that would cancel to just like 1 over S plus 1. And 1 over S plus 1 is like easier to do L inverse of, right? But I have S over S plus 1 squared, which is like I am just like not sure how to do that. So what we have to do instead is break it up. So I'm gonna break up S plus 2 into like S plus 1 plus 1. So that would actually make this S plus 1 over S plus 1 squared plus 1 over S plus 1 squared. So this is now easier to deal with because I can just cancel those and just be left with 1 over S plus 1. Okay. So L inverse of 1 over S plus 1 is what we have over here. What's L inverse of 1 over S plus 1 squared? Well, this is like a translation of 1 over S plus 1, of 1 over S squared, just by 1 unit. So whenever you have L inverse of like a translation of something, you want to apply the translation theorem. So e to the at times L inverse of f of s. So this would be e to the negative 1t times L inverse of just 1 over s squared, basically. And L inverse of 1 over s squared is just t. Okay. Let's bring this along. All right. Now, what is L inverse of 1 over s plus 1? This is just e to the negative t. Okay. That's just in the table, straight up. And this one is, this one's going to be a little bit weirder, but whenever you see e to the negative 2s, you're going to want to use this formula right here, which we kind of discussed earlier. So this. So this is going to be L inverse of 5 over s plus 1 squared evaluated at t minus a. So a is 2 in this case, and then times u sub 2 of t. Okay, so yeah, so you do L inverse of whatever your inside thing is, but then once you figure out what this is, then you evaluate it at t minus 2, and then you multiply that by u sub 2 of t, where like a is just 2 in this case. Okay, so then L inverse of 5 over s plus 1 squared well, we basically already did this. L inverse of 1 over s plus 1 squared is equal to e to the negative t times t. So this is going to be 5 times that. But the catch is that instead of using t's, we want to use t minus 2's. So this is e to the negative t minus 2 times, instead of t minus 2. So anytime I see a t, I just replace it with t minus 2. Okay, cool. So this would be our answer. Cool. All right, easier problem. Use the definition of the Laplace transform to show that the Laplace transform of t is equal to 1 over s squared. All right, definition of the Laplace transform, you should just know this one. This one is not on the formula sheet. It is equal to the integral from 0 to infinity of e to the negative st times whatever your function is, which is t, and then dt. So you got to do integration by parts here. U is equal to t, du is equal to, du is equal to 1, dv is equal to e to the negative st, and then v is equal to, this is like with respect to t, right? So then v is equal to 1 over negative s, e to the negative st. So this is equal to uv, so negative t over s, e to the negative st. And I'll do that from 0 to infinity, minus the integral of v du, which would be negative 1 over s, so I'll pull that out here to make that positive 1 over s, e to the negative st dt. So negative t over s, e to the negative st from 0 to infinity, plus 1 over s. Well, this is going to be actually minus 1 over s squared, e to the negative st. Just integrating that, I have to divide by negative s again, so I get negative 1 over s squared. And then that's from 0 to infinity. Might as well just combine these into just one thing where I'm evaluating everything from 0 to infinity. And so now this is, so I can't plug in infinity. I have to do a limit as b goes to infinity and just like let b take the place of infinity. So I get t over, sorry, not t, b over s times e to the negative s times b. Or that would actually be positive now. So I'm putting, so I want to put this into my denominator here. So to do that, I want to make this this exponent negative. And then minus 1 over s squared e to the positive s times b. All right, so that's what I get there. And then minus what I get when I plug in a bunch of zeros. So I'll get 0 over s times e to the 0, and then minus 1 over s squared e to the 0. All right. This right here, this is just going to go to 0. This right here, we're going to have to do L'Hopital's rule on that one real quick, but that's going to be b goes to infinity. So because I have like an infinity over infinity situation, so if you do L'Hopital's rule, you take the derivative of the top and then the derivative of the bottom. So the derivative of the top would be just negative 1, and then the derivative of the bottom would be s squared times e to the sb. We're taking a derivative with respect to b here. And so now this is going to go to 0. This is already 0, and then this over here just becomes positive 1 over s squared. So this whole thing is just equal to 1 over s squared. All right. Compute the Laplace transforms of the following functions. T squared plus 1. First thing you want to do is actually like square this out. So this is t to the 4th plus 2t squared plus 1. And so the Laplace transform of this just do the Laplace transform of each of these terms. The Laplace transform of t to the 4th is 4 factorial over s to the 5th. Laplace transform of 2t squared is 2 factorial, which is just 2, over s to the 3rd. And the Laplace transform of 1 is just 1 over s. By the way, 4 factorial is just equal to 4 times 3 times 2 times 1. So 4 times 3 times 2 is 4 times 6. So that's 24. Might as well write it like that. Also, 2 times 2 is 4. All right. E to the negative t minus sinh of 2t. What do we get for that one? Okay, this one's like a little more straightforward, right? This one's just kind of applying the table. So the Laplace transform of e to the negative t is 1 over s plus 1. And then the Laplace transform of sinh of 2t sinh of 2t would be, so k over s squared minus k squared. K over s squared minus k squared. Yeah, I think that's it for that one. All right, t cosine of t over 3. So cosine of t over 3 is something we can do. When you do t times cosine of t over 3, that's when you want to do this formula here. So you just want to do the Laplace transform of whatever your function is, and then just take the derivative of it and then make it negative. Okay. So this is equal to negative dds of the Laplace transform of cosine of t over 3. I'm going to write that as like 1/3 t. Just so I can like more clearly see my k value here. So this is negative dds of the Laplace transform of this. Cosine of 1/3 t, I believe, is equal to s over s squared plus 1/9. And so now you just have to take the derivative here. Yeah, just checking my formula for cosine. Okay. So this is going to be negative. Now I just do a quotient rule. Derivative of the top is 1, multiplied by the bottom, minus top times the derivative of the bottom, which would just be 2s, all over the bottom squared. All right, you can simplify that if you want. I'm just going to keep it. All right. Laplace transform, or L. Sorry, we're just doing L, not L inverse. All right, L of e to the negative 2t times cosh of t thirds. So this is a translation theorem. When I multiply by e to the negative 2t, I figure out what the Laplace transform of f is, and then I just plug in s minus a instead. So I do L of whatever cosh of t thirds is. Do the square brackets. And then I plug in s minus 2. Wait, is it s minus 2 or s plus 2? Let's look at the formula. I think it's plus. Yeah, so if you have e to the at, then you do f of s minus a. So I have e to the at. So a is negative 2. So this would be s. Wait. Yeah. So e to the at, and then s minus a. So s minus negative 2. So s plus 2. E to the negative 2t, and then f of s minus negative 2. All right, good. All right, what's cosh of t thirds? All right, cosh of t thirds, s over s squared minus k squared. So s over s squared minus 1/9. But then instead of s, I should plug in s plus 2. So every time I see an s, I replace that with s plus 2. Okay, so just replace all your s's with s plus 2's, and that would be your answer. All right, inverse Laplace transforms. Compute the inverse Laplace transform of the following functions. All right, so this one right here, we're probably just going to have to expand everything out. So 1 over s plus 1 over s squared plus 1 squared would be 1 over s times 1 over s. Plus, and then we'll do 2 times the cross term, which would be 1 over s times 1 over s squared, or 1 over s cubed, and then plus 1 over s squared times itself, which would be 1 over s to the 4th. So L inverse of this whole thing is equal to L inverse of each term. What's L inverse of 1 over s? That's just t. Let me just write this as just 2 over s cubed, because what is L inverse of 2 over s cubed? Well, this just happens to be t squared, actually. The Laplace transform of t squared is equal to 2 factorial over s to the 2 plus 1, which exactly fits this. And let's maybe do this last one in multiple steps. So if I have 1 over s to the 4th, I would like that to be like 3 factorial over s to the 4th, because then that would like more clearly fit this formula right here. So L of, I don't know what happened with this. Why is that not curly? All right, L of like t to the 3rd is equal to like 3 factorial over s to the 4th. So that's like almost what we got here. So we have to, if we want this to be a 3 factorial in there, we have to divide by 3 factorial. 3 factorial is just 6. So that's 1 over 6 times L inverse of this thing, which is just t to the 3rd. All right, 1 over s to the 4th minus 9. This, I think what you want to do here is factor this as s squared minus 3 times s squared plus 3. And then write this as a over s squared minus 3, or as plus b. And then plus cs plus d over s squared plus 3. So do a partial fractions thing on this, and then this would be something you could do L inverse of. This will be something you could do L inverse of. Maybe you could also do a convolution theorem on this one. What would L inverse of s squared minus 3 and plus 3 be? Yeah, you probably wouldn't want to do a convolution theorem on there, because yeah, if you had like it was 1 over s squared, yeah, so 1 over s squared plus 3, that would be like a sine of kt thing, and then 1 over s squared minus 3 would be like a sinh of kt thing. So you're probably not want to do the convolution of like sine of t and sinh of t. That would probably get like really messy. So this is probably the best way to do this. All right, so right side, as plus b times s squared plus 3 plus cs plus d times s squared minus 3. So this is as cubed plus b s squared plus 3as plus 3b plus cs cubed plus ds squared minus 3cs minus 3d. Gosh, okay. So a plus c has to equal 0. B plus D has to equal 0. Three A minus 3C has to equal 0. That's weird. Okay. And then 3B minus 3D has to equal 1. Cool. This one right here says that A is equal to negative C. This one right here says that 3A is equal to 3C, which would, if you divide by the 3, that just tells you A is equal to C. If A is equal to C and A is equal to negative C, then A and C both have to be equal to 0. Okay, you could also see that by just like, sub in A over here. That would tell you that C is equal to negative C. The only way you can do that is for C to equal 0. Okay, B plus D is equal to 0, and so B is equal to negative D. You can sub that in over here to get that negative 3D minus 3D is equal to 1. So negative 6D equals 1. So D is equal to negative 1 over 6. So B is equal to the opposite of that, which would be 1 over 6. So this is equal to 1 over 6 times 1 over s squared minus 3 plus D, which is negative 1 over 6, times 1 over s squared plus 3. All right, running out of space. I'll just use up more space. L inverse of 1 over s to the 4th minus 9 is equal to L inverse of this which is equal to 1/6 times L inverse of 1 over s squared minus 3. Okay, so this is like s squared minus k squared. So our k is the square root of whatever is here. So like our k is like the square root of 3. So we're going to want to divide by the square root of 3 and then multiply by the square root of 3. This is like L inverse of square root of 3 over s squared minus 3. or s squared minus square root of 3 squared. And then minus 1 over, I'll do the same thing over here. L inverse of square root of 3 over s squared plus 3. Okay, and then yeah, L inverse of s, or of like k over s squared minus k squared is sinh, and k over s squared plus k squared is just sine of kt. So this is 1 over 6 root 3 times sinh of square root of 3t minus 1 over 6 root 3 times just sine of square root of 3t. That would be your answer. All right, so this one was pretty long and involved, but that's how you do it. So we're just going to shrink it a lot, whatever. All right, e to the negative 2s times L inverse, or sorry, times 1 over s squared. So when I multiply by e to the negative 2s, what formula? Doing this formula, I'll just bring it up. So do this formula. So this is equal to L inverse of just whatever this thing is. So I do L inverse of 1 over s squared, but then I evaluate it at t minus a. A is just 2, so t minus 2. And then multiply by u sub 2, or u sub a, which is u sub 2. L inverse of 1 over s is just t. So L inverse of 1 over s, just, evaluated normally at t. Sorry, 1 over s squared. That's just equal to t. And so if I were to do like t squared, that would be like t squared. And if I were to do t minus 2, it would be t minus 2. So this is equal to t minus 2 times u sub 2 of t. All right, 4 over s squared minus 4s plus 20. This one, you're going to want to do s squared minus 4s. All right, I just kind of know that I want to do it like that. Okay, so you want to do completing the square. So figure out like completing the square however you want to do it. I'm just sort of recognizing this like s squared minus 4s as like it's almost like s minus 2 squared. S minus 2 squared is equal to this. This is s minus 2 squared, right? So I could factor this as s minus 2 squared, right? So if I like pull off a 4 from this 20, then I get s minus 2 squared plus whatever's left over, the 16. Okay, and so I get 4 over s minus 2 squared plus 16. And so that's a translation of something. So this is, we're going to have to do this thing over here. L inverse of f of s minus a. So if I have a translation of something I already know how to do, this is equal to, well, I could just translate it back. So this is like, so a is 2 here. So this is e to the 2t, what's that, times L inverse of just 4 over s squared plus 16. 4 over s squared plus 16, I think that's sine of 4t. 4 over s squared plus k squared, yeah, that would be just sine of 4t. Straight up. All right, so that's how you do that one. Row reduction. All right, cool. So how do I do row reduction on this guy? You can just translate this into a matrix. an augmented matrix rather, and then you just do your row operation. So I can do, what's the best way to do this? This is already terrible. I'm gonna do, I can just scale the first row by 2. So 1/2 row 1. So 1, 2, -3, 5, -1, 2. Now I can add -5 times row 1, add that to row 2. So row 1 stays the same. And then I do -5 times everything up here and add it to this. So -5 times 1 plus 5, that's 0. -5 times 2, that's -10. -10 added to -1, I get -11. -5 times -3, that's +15. Added to 2, I get 17. All right, we're going to start getting fractions here. I'm going to divide row 2 by -11. So we'll get -17 over 11 here. That's fine. Then I'm going to add -2 times row 2, add it to row 1. -2 times -17 is 34. So I'm going to add 34 over 11, add it to 3. So this is, that's actually not as bad as I thought it would be. This is just straight up equal to 1, 0, 0, 1. This is -17 over 11. This is almost 3 and 1/11. 34 over 11 is equal to 3 plus 1 over 11. And then 3 plus 1 over 11 minus 3 is just equal to 1 over 11. All right, so this tells us that x is equal to 1 over 11 and y is equal to -17 over 11. You could check that very easily just by plugging x and y into these equations. I'm tired and this video is going on too long, so I'm not going to do that. Eigenvalues. You want to just take the determinant of a minus lambda I, which is just 0 minus lambda, 2, 3, and then -5 minus lambda. So then I do the determinant. I get negative lambda times -5 minus lambda minus 2 times 3. So this is 5 lambda plus lambda squared minus 6. Or I could just write this as lambda squared plus 5 lambda minus 6. I'm just going to do that like that, just so factoring just is easier on my brain. So this is lambda plus 6 times lambda minus 1. If I did that right. Yep, 6 times -1 is -6. And then 6 lambda minus lambda is positive 5 lambda. So lambda is 1 or -6. So those are eigenvalues. So now we do lambda equals 1. And then I take a minus 1i. And that is equal to, so I usually just kind of look at that and then just subtract 1 along the diagonals. So -1, 2, 3, -6. And then I do 3 times the first row, add it to the second row. And then I just get 0 zeros for the second row if I do that. And so this would tell me -x plus 2y is equal to 0. So I can pick x to be 2 and y to be 1, and then this equation would work. So I would get -2 plus 2 is equal to 0. So then our eigenvalue, or eigenvector, would be 2, 1. And if I do lambda equals -6, a minus -6 times I would be equal to, just add 6 along the diagonals, and I would get 6, 2, 3, 1. So I could just add -2 times row 2, add that to row 1. I get zeros up here, and I can say 3x plus y is equal to 0. So I can make x equal to 1 and then y equal to -3, and that would solve that equation. So our vector or eigenvector would be 1, -3. Holy crap, that was a long video. Yeah, we're done. So let's maybe just kind of talk about some of the things. Yeah, the exam, I worked through the exam like a second time earlier today. It's not gonna look like this one. This one sucked. So this problem sucked. Maybe don't worry about that one too much. Let's see, how was that one? This one was mostly fine. I probably wouldn't ask you to do like two different methods. I would probably ask you like, do you know how to do the convolution method, or do you know how to do it just like in one way, right? So you should know how to do both, but I probably wouldn't ask you to do both. Solving IVPs, you should know how to solve an IVP. I would probably not give you the most complicated one in the world. So I'd, yeah, like, I don't know how much more I could like really say about it, but like, yeah, just kind of know how to do them. I feel like it's likely that I made like some sort of like computational error or something somewhere in this video. So if you catch something, please just like throw it in the comments, and just so other people can kind of see it, just because like, not a lot of time here. More, you should probably be more concerned with like the main ideas from these anyway, as opposed to like small computational errors. If there's a big error or something like that, like definitely like say something, but like hopefully there's nothing like too crazy. Definitely know the definition of the Laplace transform. This is not on the formula sheet. This is the only thing that's not on the formula sheet, just because I think it's that important that you should actually know it. Yeah, definitely know how to compute like a variety of things. Like, you're getting a crap ton of formulas, but if you don't know how to use the formulas, like, you're just kind of like, it doesn't do anything for you, right? So don't go in just being like, oh, I could just use the formulas. Like, applying these formulas, it really is more complicated than just kind of like looking at what it says. Like, for example, like this one right here, like on like one of the previous quizzes, you needed to like use this this formula, and just like no one really knew how, like, what this meant. They thought that like this was like a multiplication by t minus a, but this is like a composition of functions. It's not like multiplication. So make sure that you like actually understand how to like apply all these formulas. Yeah. Anything else? Eigenvalues, eigenvectors. Yeah, it's just kind of a lot of formulas and a lot of algebraic manipulation. So practice makes perfect with these things, and errors are, likely and common, honestly. So, I'll understand that when I'm grading these things and all that. So good luck studying. Hope this helps. Sorry if this was too long. It was probably too long. I'm tired. I'm gonna go eat food and go to bed. Have a good day.